Welcome everyone to this special talk that we'll be giving here today. My name is Christoph Schroeder. I'm VP of Software at Lumina Technologies. Today I'm going to talk to you guys about the undiscovered value of autonomous drive, how technology deployed in cars capable of highway pilot technology can actually enable and support level 0 active safety features and enrich everyone's lives from the get-go. Before we dive into the presentation, let's take a look at a few company highlights and take a look at what we have done at Lumina Technologies in the past. We have built a LiDAR sensor from scratch, not used off-the-shelf components, but actually purpose-built all of the pieces that are necessary to build a LiDAR sensor that can reach both performance as well as cost targets. With that sensor, we are going to deploy it into serious production and going to deploy it with our lead customer, which is Volvo. The goal there is to deploy it in 2022 and actually build highway pilot features in serious production vehicles. Besides having a partner in Volvo, we actually have 50 additional customers, partners that we work with. One specific one that we like to mention is actually Daimler Trucks. Daimler Trucks and Torc work on highway autonomy for trucks and try to automate trucks to deploy it into serious production very soon as well. With them, we have a second customer that actually is going to productize the technology. One of the special things about the setup of our company is that we actually look at both hardware and software at the same time and try to combine it and deeply integrate things so that we ultimately reach the best possible performance. We focus on 3 different verticals. We focus on passenger cars, we focus on trucking, as well as robotaxis. All of those verticals have different needs and different requirements in terms of the features and the functionality, but the great thing about our technology is we're able to support all of them with one single architecture. Building on top of our LiDAR system, Iris, we also have the perception components needed to actually detect things and classify things, like for example detecting pedestrians, detecting cars, detecting trees, detecting traffic signs, detecting lane markings. All of those things you need to know if you want to build a decision-making and path planning system. The better our perception system is, the better and easier the decision-making and path planning will be. At Lumina, we focus on highway autonomy. We don't believe that urban autonomy and robotaxis will come anytime soon, but highway autonomy is something that will come very, very soon. And our technology actually enables it. We work on semantic segmentation, object detection, classification, lane and road tracking, as well as velocity measurement, and are able to adjust the field of view dynamically based on where we are and how we're driving. If we're going up the hill, we actually look up the hill. If we go down the hill, we actually look down the hill. Our software enables reliable detection, reliable classification, even at long ranges. Over-the-air updates keep it always fresh, always up to date, always able to detect the newest things, to classify things that it has never seen before. With all of that combined, we will be able to enable highway autonomy and put those cars on the road. So let's take a look at the building blocks. The first building block in order to get to autonomous driving like level 3, level 4 is to look at active safety, and what we usually call level 0, where the driver is in control and the system really just corrects and reacts and supports the driver. The other building block is driver assist features, like for example distance keeping, lane keeping, and all those lower level features. We call them level 1, level 2, level 2 plus features. You actually get those immediately across the board. So when we look at the different capabilities and we talk about the additional value of autonomous driving, we actually need to talk about the safety value add and the things that we do in addition to autonomy, in addition to enabling people's convenience and helping them to get from A to B quicker. We will substantially improve AEB, emergency braking features, dramatically improve safety with detecting small objects really far out, detecting free space, enabling steering, automating steering, emergency steering functions. Doing that, what we call proactive safety, will actually help to save lives. So when you look at level 3, level 4 autonomous driving features, you need to look at it from the 2 different streams that we have. Right? Level 0 is the stream that talks about proactive safety, where the driver is still in full control of the vehicle, where the vehicle really just mainly corrects the driver in emergency situations and tries to support to prevent accidents. And then you have your performance stream, that is the ADAS functionality, right? Your level 1, level 2, where the driver is still in full control of the vehicle. The vehicle steers, the vehicle accelerates, so the vehicle does partial automation and a few tasks, but ultimately the driver is still in control. Having those two different streams combined at some point gives you your autonomous driving set and vehicle, but the orange boxes on the slide here are actually what is going to enable it and what is going to give immediate value to everyone from day one when those cars are deployed. When you look at how the operational design domain grows for automated driving features like traffic jam pilot and highway pilot, you really need to look at something like this. Omega is basically everything, right? That's the whole world. It's you sitting in the car, driving off your parking lot or your driveway into the world. From that moment in time, proactive safety already helps you and already works. It's level 0, it works everywhere, there is no restriction on ODD, it corrects your mistakes, it helps to prevent accidents everywhere. Beyond that, in a slightly smaller operational design domain, you have your driver assistance systems features, like for example, what we used to see on the road is being called pilot assist or autopilot features, things like that. They work in a certain domain, not everywhere, but in a certain domain, right? Like for example, on highways, on urban roads, on rural roads. It supports you, it helps you to drive, but ultimately, obviously, doesn't do the entire driving task, only part of it, supports the driver in his driving task. And then you have this very small operational design domain, and probably on the slide it's already a little too large. Because initially it will be really small. It will be probably only highways, probably only different locations, probably only different pieces of a highway, where you actually will have highway pilot functionality and will be able to relieve the driver, where the car takes full control of the vehicle and the drive, and the car does all the driving necessary, where the driver actually can lean back and read his newspaper. That's just going to be a small fraction of all the situations and of all the different driving situations that you might have. But the Omega, the entire world, the entire operational design domain will benefit already from the technology that is built into the cars to enable automated driving by improving proactive safety. So that's the opportunity, right? ADAS can and must improve. Today we see systems like that. That's a AAA study from 2019, one of the probably most advanced ADAS systems out there, and in most cases, most as in way above 80%, the pedestrian has not been detected and has not been avoided, and the car did not stop. Why is that? Well, it's to a big part because of the sensing technologies embedded into those vehicles. It's to a big part because of the difficulty to actually predict things. And the difficulty to predict things also depends on the difficulty to see, classify, and measure the world around you, right? So it's all about perceiving what is going on. It's all about seeing. It's all about how well you see your environment. Take an example. Take the example. You sit indoors. It's dark outside. You have your curtains closed, and you try to peek through. Right? That's comparable to how radar sees the world. Right? You get like very tiny little glimpses of what is going on around you. But now imagine what happens when the sun dawns, it's sunny outside, shining, you open the curtain and you suddenly see the entire world, you suddenly see all the fidelity, the depth of the world, everything that's going on, you understand all the details much better, right? That's the difference between legacy sensors, traditional sensors like radar in those cars and our technology, our LiDAR technology, our iris technology, and just by looking at that, you can understand how much the performance of those features can actually be improved. So that's our vision, right? We want to prevent all forward collisions. Most of them actually are caused by human errors, and most of them fall into categories that can be attacked quite easily with really good emergency braking systems as well as emergency steering systems. For example, reaction time and unsafe distances to the lead vehicle, something that can be really, if you have confidence in your measuring and perception system, can be really avoided. suddenly appearing objects, things that jump in front of you, like the famous child in between the row of parked cars that jumps out and tries to catch the ball, grab the ball that is on the ground. Those can be avoided. Those accidents don't have to happen. If you see everything, if you have this very precise, high definition picture of the environment and know exactly what is ahead of you, you are able to react to those. And low velocity collisions on parking lots, for example, things like that, something that can also be in most cases really avoided using the technology. And how current systems actually work and are being rated, we see on the next slide. So there are three major categories for NCAP tests that are being looked at. One is approaching a stationary car, right? So you're in your ego vehicle, in front of you there is another car. It's stationary, so velocity is 0, and you approach it, and the question is, at which velocity is the car still able to detect it and then brake and come to a standstill. And looking at like industry-leading systems, you see that 30 miles per hour is actually possible, 40 miles per hour is possible, but beyond that it actually gets really difficult. Beyond 40 miles per hour it's really difficult to actually see it early enough, brake for it, and then come to a standstill. Our technology will help dramatically to improve that. Why? Because we do two things at the same time. We can measure objects as well as lane markings and make that determination whether something is a blocking object in our lane or just something beside the road really quickly and much more reliable than has been done so far. The other kind of test that is being usually used is the target switching to a stationary car. Right? So you have a stationary car somewhere in front of you, and then you follow a lead vehicle, and the lead vehicle at some point cuts out, and then you see the stationary car in front of you, and then the question is, how quickly can you actually react to it? Can you come to a stop? And that's obviously a more challenging task than the one before, because you only see it very late, the stationary vehicle. So you see that the system that performed quite well in that original task and was able to stop at 40 miles per hour, now only is capable of doing that up to 20 miles per hour. And really just because of the latency in the situation and the way how things work. Right? So having a high measurement rate on one hand side, but very precise and very robust measurements on the other hand is key to actually solving that in a much better way. The third test case is approaching a slower moving object, right? So something that is not stationary but actually does move. It does move with a certain velocity, and then the question is, how much faster can you actually be so that you still get to a standstill? So that's an even more difficult task because now everything is moving and everything is behaving and needs to be predicted somehow. And you see that the state-of-the-art system that we looked at here, that has been looked at here, is capable of reducing velocity from 40 miles per hour, but not anymore from 50 miles per hour delta velocity, right? And that's again being able to measure the velocity, being able to do it robustly, to do it reliably, all of that kind of cumulates in the capability of actually reacting to that situation properly. And that's what our technology is going to enable. So ultimately what we believe in is that we can actually be 7x safer than what we see out there right now with today's system. And by doing that, you will be able to do many things, saving lives, improving people's health and safety on one hand side, but also think about different business models and possibilities to leverage that capability. Right? Today, a huge cost of the total car ownership actually goes towards insurance and towards all the things you have to pay for when there is an accident. If you have way fewer accidents, then that can enable completely different approaches with insurances and maybe subsidize the technology to ultimately really give back to society and improve people's lives and safety. So looking at the insurance opportunity, you see many different possibilities there, right? You can unlock attractive economics and subsidize the technology and really foster deployment of LiDAR sensors, foster deployment of the technology, and thus really make the world much safer than it has been so far. And ultimately, it's really the total cost of car ownership that is important, and that is what we need to optimize for. Right? That's from a business point of view the key topic here. In order to build a system that is actually capable to solve those details and support the functionality and improve it the way how we propose here or believe we can, you need to solve for a lot of different requirements. And when you look at the slide, the upper row is actually the functional requirements, the lower row is the non-functional requirements, and both of them are actually equally important. When we talk about functional requirements, we talk about things like range and resolution, which are the two key requirements, right? If you just have range but no resolution, then you get 1 point on the target really far out, doesn't help you at all. If you only have resolution, you get a lot of points on a target close by, but don't see things far out, so it doesn't help you at all. You need both. You need high range, long range, you need high resolution in order to get enough points on a pedestrian, for example, and be able to detect it. Fidelity is important, right? Your data needs to be really precise. The frame rate is important in order to be able to quickly react to things. The field of view is important, right? If you look like that only, then you'll be able to see half of it. If you look like this and have a 120 degrees field of view, for example, then you'll be able to see much more. Weather is a key component, right? Just working during daytime when it's sunny isn't really going to solve all of the corner cases. You actually need to work during nighttime, for example, when it's a little rainy and things like that. We believe there will be many systems out there at the same time talking to each other and interfering with each other. So you need to figure out a way to mitigate or limit or eliminate interference. Right? Those are the functional requirements that are key. But again, it doesn't work without the non-functional requirements, without being able to produce it at low cost, without being able to produce it in auto-grade quality, without being able to build something that is safe for humans around it, that has a scalable architecture and so on. And by building our iris sensor and building it from scratch, we actually solved for all of those without having to build a Frankenstein LiDAR, but actually something that is really cleanly integrating and solving all of the different requirements. I actually emphasized range and resolution, and I want to take another minute to kind of emphasize it a little bit more. You see on the left-hand side, if you had a 45 points per square degree resolution at 200 meters, you would actually get 2 points at most on a motorcycle, which is pretty much, I mean, you can't detect a motorcycle with that little points. On a pedestrian, you would actually get 0 points. Obviously, you can't detect that as well. If you have 300 points per square degree, which is what Iris is capable of, then you actually get 15 points on a motorcycle, which gives your software enough points to comfortably detect it, but also classify it as a motorcycle and quickly be able to react and do the right thing. Same with a child, right? You get 6 points on a child, at least in some cases even more, if you have 300 points per square degree, which is again enough to detect it, to react on it, and to make the right call. And on the right hand side, you see the current other companies in the LiDAR market, what their point density versus range looks like, and what the requirements are for our different use cases and our two products. Hydra is the product that we're currently selling towards test and development fleets, and Iris is our serious production product that will go into serious production with Volvo, that will be able to see 250 meters at a 300 points per square degree resolution and actually enable those features that we see on the left-hand side. Today's systems only consist of two sensing technologies. One sensing technology is radar, the other sensing technology is camera. Originally, Level 0 systems started off with radar, and then cameras have been integrated to it. And when you look at the chart here, you see all the different categories and how those rate with respect to what is needed and with respect to what Iris is capable of doing. Current systems that you have out there have their strength and work well in certain cases, in certain environments, for certain use cases and driving conditions and driving situations. It's just that they do have a lot of functional insufficiencies and things that don't work well, that actually limit the performance of the overall system. Right? Let's take an example. For example, the radar has a very hard time seeing lane markings. Basically, it doesn't see lane markings. Has a very hard time detecting pedestrians, has a very hard time detecting contours of objects. Why? Because resolution isn't good enough, because pedestrians don't reflect enough. There are many reasons why the technology itself is inherently flawed and has insufficiencies just in the way how they perceive things. Same with the camera. The camera works really well for a lot of use cases. Like, for example, lane markings can actually be detected really well in the camera. The only drawback is the range, right? You don't get that far range. You are able to detect objects like pedestrians, cars, traffic signs, and many other things in the camera really well when the weather is good and at day. During nighttime, things get more difficult. When it rains and snows, things get more difficult. If it's foggy, things get more difficult, right? So there are always trade-offs. When you combine those two, things work better and you are able to build a decent system, but still, it's no match and nothing that can be compared to what Iris will enable in terms of detection performance, classification performance, as well as SOTIF performance, which means really doing the right thing. Not just doing what the requirements say, but actually doing the right thing by basically eliminating false positives and negatives. So I've talked a lot about how it looks when you open the curtain and suddenly see the world with a completely new fresh eyes. So let's take a look at some of the pictures and images and point clouds that we're able to create. What you see here is just a standard point cloud. It's actually nothing very special, recorded at 100 points per square degree. What you see here are the different colors that depict the type of object. So if something is red, it's the ground. If something is blue, it's the background. If something is orange or actually pink, it's a vehicle. And if something is green, it's the lane markings ahead of us. Right? And you see that we're able to see the ground, for example, up to 75 meters ahead of us. We see lane markings up to 150 meters ahead of us and see objects even 250 meters ahead of us, which actually gives you enough time to react to them and enough information and density to actually make the right call in order to build something that is more robust than what you've seen so far. The great thing is it doesn't just work in good weather conditions during daytime. It also works at night the same way as it does during day, and it's also able to penetrate rain. What you see here in the right lower corner is the camera image, and you see it's quite rainy, right? It's probably moderate rain, something like 100 millimeters per hour, and the lighter point cloud that you see in the upper right corner actually looks really good still. You see ground, you see the overpass, you see objects really far out. We zoomed in a little bit, and you see actually cross traffic at 191 meters, for example, and you see all the objects that you need to actually react to them. So yes, performance is slightly degraded during rainy situations, but it's still good enough to actually detect everything and make the right call. Our perception system does many things on top of the data. One thing that we do is, as we've seen before, is really on point level classify everything, right? On point level, make sure we understand each return is a return from either a car or a pedestrian or a lane marking or the road or some background object or traffic signs, things like that. Lower left side, you see the lane markings, lane geometry. That's something that is actually really important to measure instantaneously in the vehicle. And what we do there is we actually create instances for the lane markings and classify them accordingly. We can classify them whether they are dashed or dotted lines, whether they are solid single or solid double, even classifying based on color, whether it's white or yellow, is something that is possible. On the left-hand side, in that image, you see the purple lanes are the ones that are solid, and the red ones are the ones that are dashed. And you see the detection range is really far out, 120, 30, 40, 50 meters, but we look into details on the next slide. In green, right next to it, you see the data tracked over time, which ultimately really gives us more confidence about everything going on. And on the right-hand side, you see the image that basically shows how we measure instantaneous velocity. By understanding the sensor, how we do, and by being able to scan the way how we need to, the world, we actually enable our system to get many points on target, and from that enable the system to extract instantaneous velocity information for each object that we have ahead of us. That feature obviously helps tremendously with things like braking for objects that are stationary really far out, because you get the velocity really instantaneously. But let's take another quick look at the lane detection performance and how that compares and how important it is. So you have two different situations here, right? Lane and road edge detection. Again, the colors are the same as before. Pink means it's the solid lane marking on the side, and red means it's the dashed lane marking. And you see the camera images next to it. On the left-hand side, you actually see, and we see the lane markings out to 145 meters, and the two cars ahead of us are the ones right next to us at the lower part of the screen. On the right-hand side, we even see them way farther, and you see the slight bow and slight curve in the pink lane marking on the left-hand side. That really reflects the real road geometry. You can't even tell from the camera image, right? You can't even see in the camera image that far out that there would be something like that. And one of the key tasks for the systems, and that kind of ties us back to what we said at the very beginning, one of the key tasks is to detect whether something is actually in our lane and whether we need to brake for it or not, right? And one of the most important things to do is to actually figure out, is that thing in our lane, or is it in a neighboring lane, or is it just partially overlapping with our lane? And the difficulty that usual systems have is they have two different sensing modalities that do two different tasks, right? The radar usually detects the object, the camera the lane markings, and then you need to somehow overlay them and do object to lane association. And by doing that, you introduce a lot of error into the system, because you cannot look around the curves, for example. You don't exactly see what is going on. With our system, we actually have one frame, one image that gives you both data. Right, so at 80 meters, the car in front of us, here circled in blue, in the camera image, it's really hard to figure out, is this in our lane? Would we have to brake for it or not? When you look at the LiDAR plot, in 80 meters, you actually see the lane markings. You know it's dashed lane markings. You zoom in and you understand that this object actually is in your lane and not the neighboring lane, and that if it would be stationary, you would have to brake for it. Right? And doing that, you enable your system to much better, much more robustly detect those things and react to them than they would have been able without it, with more traditional legacy systems. So having talked about all the different features and possibilities, let's sum things up. We can improve advanced active safety dramatically. We have much more reliable detection of objects and debris on the road. We actively measure free space. We actively detect objects even in shadows and all lighting conditions, right? Doesn't matter whether the sun is shining, whether it's dark, whether there is a shadow on the road or not. LiDAR iris technology is able to detect that. We have precise distance and frame level velocity measurements. And if you combine all of that and look back at the different features and different corner cases and the different things that we looked at in the beginning, then it's quite obvious how this new level of perception, this new level of understanding what is going on, this new level of perception of the world around you, how that's supporting and improving the feature set that is being deployed these days. With that, thanks a lot. Please visit us at luminatech.com for more information. Bye.